All right, welcome everybody.
Hi, Professor.
Hello, how are you doing? Thank you for that. That's great. Were you guys throwing paper balls or something?
He threw it at me. He's fighting it.
Okay, all right. Yeah, well this is great. Yes.
Oh, I think I asked you this at office hours. When are we getting next exactly?
So the person who is primarily in charge of that told me that they are about halfway done.
Woo!
Okay.
How they looking?
I didn't ask for statistics.
Is it not you?
Huh?
Is it not you?
It's not. We have a grader.
We have a guy.
We have a grader. So no, the way. So just as a note, the way it works, right, is you'll get your exam back, right, and if you want to, contest the grading, you'll be able to do so. Okay, and what we'll have another assignment on Canvas where you can upload your photocopy or your scanned exam, and then write why we should be giving points. All right, so that's how we do it. So we go back and forth. And also, that's that and for ABET, we also do scan a fraction of the exams so that we have them for record, right? So, yes.
Wait, so we're getting it back scanned, not physically?
No, you'll get it back physically. You'll get it back physically. But I'm also telling you that we scan some of them so that you don't do anything, that might. Well, we have done all in the past. We can consider that. We can consider it. But it's actually, you are a big class. And so that makes it a little bit trickier. Okay. Other questions? Yes.
Do we get it physically here or in your office?
You'll get it here. Don't worry.
Alright, thank you.
You'll get it here. Okay, good. No, okay. So there's one other announcement. Okay. If you're a sophomore, you may have got this email from Lena, and what we're saying is that we have an orientation tonight, right after this class, 7:15. Okay. Yeah. So if you have questions or suggestions about the curricula or opportunities, we'll be there. Okay. You're still welcome to participate. Okay. This is a meeting of no. So you should have gotten an email if you're a sophomore. If you're a sophomore, you should have gotten this email that says, "Please save the date for the upcoming sophomore student orientation." Okay, and so that's at 7:15. So it's going to be a few professors, right, that are going to be answering questions and presenting a little bit of information out from the department. Okay. About the curriculum. Okay, so if you have questions about credits, about what counts for this or that kind of stuff. Okay. So what we're going to do, we're going to jump right in to a fun example. All right. We talked about this last time, but there are kind of four big equations that we want to keep in mind. Okay. One is about the relationship between an external distributed force along a beam and distributed force along a beam, and what does it relate to? Huh? No, there's no torsion. Transverse loading of a beam, okay? Huh?
Shear.
Yes, who said that? Did you say that? Thank you. All right. So we're talking about beams. Oh, not beams. Beams. Okay. And these are transversely loaded. And we kind of already went through this, but they're kind of four big equations. Okay? So the change, the derivative of the internal shear force with respect to x, or it's moving along the axis, right? The longitudinal axis is equal to W. So this is a distributed force. And this is external. This is internal. Okay. Then we have a relationship for the moment and the internal moment and the, yes. Okay, these are both internal. Okay. Then we have a relationship for, well, we take your pick. We have either concentrated force applied or concentrated moment. So what are these equations? You tell me. We covered this. I know you know.
I don't know.
No?
I don't know.
Oh, you had a nice smile on your face.
I was waiting for you to give me the answer.
Oh, okay. Well, do you want to help him out?
Me?
Yes. So let's do the concentrated force one.
I feel like delta V is equal to W.
Close. Okay, so it's a concentrated force. And it's important to keep in mind that this, oops, let's do a different thing. Okay, so if I'm looking at what's happening, let's just say I have, my plot, and I have my V, all right? And let's say that I was here before. I'll use a different color because I can. I was moving along here. When I get to this location, it jumps, okay? And that jump is F app, or delta V. Okay. Okay. So then what's the concentrated force one, or concentrated moment? That's the fourth one. You guys tell me. It's very similar.
Couple moments.
Huh?
Couple moments
A coupled moment into the system, yeah?
is equal to delta F.
Yes. Good. Okay? Right? And I guess we should point out this is internal. This is external. This is internal. This is external. Okay, now this one's a little weird though, because it's you move it along the beam, and you have this M app, okay, and it's actually, the way we normally think of this is actually negative, right? That would be a negative moment being applied if I'm looking into it, right? Or at least if Z is coming out of the page. But with our nomenclature, all right, this is going to have a positive jump, okay, in the internal bending moment. Okay, so these are the big four. You're going to want to remember as you do graphing. Now, you're like, wait, do I really need these? Because before I could just do method of sections back in statics, and everything was hunky-dory, right? Well, maybe not, because that's also got some things to keep in mind, right? When we're doing the method of sections. This technique, though, allows us to use what we call kind of a graphical method, or we use the differential and integral forms of these equations as we're moving along. Okay? So let's do an example. Okay, and this is one of the homework problems, all right? And I might not solve every little detail of it, okay? But it should kind of inspire and help with this approach. Which way? Looks like this is. Not completely to scale. Okay, so it has length L, and it has a bending moment applied. Okay, notice this is in the which direction? Counterclockwise direction. So that means that if we look at this formula that we have right here, this will have a negative delta M. Okay, because it's in the opposite direction of here. Please note this. Now, we also have an FF. This is positive right here. And so this will end up giving us a positive jump in the internal shear force. Okay. Now, how do you start? What do you think? How would you go about starting this problem? What is kind of the first thing we do in statics or in mechanics to get to mechanics? What would be the first thing that you do? Yes, Zach. Okay, so equation, I like that. So let's look at equilibrium. Okay. Specifically, we're going to look at external equilibrium. Okay, that's going to be our first thing here. So we're going to look at it externally. And whether you do this problem with method of sections, or if you do this problem with the graphical method or differential integral equations, you're going to do external equilibrium first. Okay, so I'm going to call this reaction RL, and I'm going to call this reaction RR. Okay, and we've got, wow, that's lovely. It's a heart. Why did it do that? Okay. Okay. Anything else you want to draw? Okay. Now, do we need a convention here? Do we need to get together and agree? No. All right, we don't really. Okay, now if you look at the problem in the homework, what you're going to see is that it says something like MAP is greater than, what did I say? Like FAP over 4, yeah. Okay, now this is when we want to just kind of think about things for a minute. I don't really expect us to know the significance of this statement at this point, all right? But it kind of is suggesting that MAP is going to be big and FAP is going to be not so big, all right? And why would I pick RL to be up and RR to be down? Now you're like, well, is this really sticky? This is just a little roller there, it could pop off. Well, we're going to say the roller can pull it down, okay? Because look, if I apply a moment at this location, all All right, if I apply a moment right here, what is that? That moment is wanting to pop this right side up and is wanting to push the left side down. Okay, so there's no convention, but for the sake of convenience, I'm going to pick RL to be up because I think that's reacting against whatever moment's being applied there. And I'm going to pick RR to be down because I think it's reacting against, again, that moment. Okay, because MAP is dominant. Yes?
I don't know if I'm picturing this wrong, but isn't a ruler just like a ball?
Right. So what I'm saying is we're assuming that this thing can hold it down as well. All right? It's not. All right? So we're going to assume this is a pinned or roller, right? And it's not no moment, right? It's not applying a moment, but it is applying a force as a constraint. Okay?
But like it's just like normal, right? Just,
It's only normal. Yes, correct.
so how is it just like not attached? It's just like
That's what I'm saying. We're assuming it can. We're assuming it can glue it down. If you want, okay, you have a good point. We could put it on the top. But that looks weird.
yeah, okay.
Okay? Or we could put one on the top and the bottom. That's doable. Okay? Does that make you happier?
Yeah.
Okay. I'm using words to explain what's happening here, okay? So, what do you do now? We do equilibrium, right? And so, someone tell me what I should write. Okay, sure. We can do it at the left. Sure. So we'll do sum of the moments at the left. Okay, it's got to be equal to 0. All right, so now you tell me what we've got.
F times that distance is positive. That's in the same direction as F, which positive is also plus M minus R. That distance.
Okay, good. Now, what else?
Sum of forces.
Yep.
It's just F applied. Is that what it said?
Yep.
Plus RL minus RF.
Yeah. Okay, good. Okay, so the unknowns are RR and RL. And we've got an equation that tells us RR right here, right? So we can come over here and we'll say that RR is equal to F app L over 4. Well, actually, no. It's F app over 4, right? Because we divide by the L plus. Is that good? Okay. And then R L, okay, is going to be essentially RR minus F app, right? So that should give us okay, did I do that right? Or was I wrong? Right, so this was RL. Right? We're good? Okay. All right, so now what we want to do is think about how to use our graphical method. So let's use, yes.
So, in the problem, it's like constrained by like RL is like a pin and RR is a roller, right?
Yeah.
How can a roller like pull down on a pin?
We just went through this. We're saying that it can, all right? We're saying it's not a wall, right? It's not playing a moment, all right? But it can. If I had to put another one on top, that's fine, okay? All right, so what do we do next? Well, let's use the graphical method, right? So we're going to use the graphical method. The differential integral technique, I guess you could say. And so for doing this, what I'm going to do is doing this. What am I going to do? That's repetitive. I'm going to draw the bending moment and the shear force diagram. Or the shear force diagram's on the top right, and the bending moment one's on the bottom. Okay? Now, it's a graphical technique, but we had to do some math, and we had to do some intuition. What you're going to do, if you look at the video, or the videos, all right, what you'll see is that we are going to think about the boundary conditions. Okay? We're going to think about the boundary conditions. And the boundary conditions are going to be kind of where x equals 0 and x equals, whoa. Okay? How do you do this? What you do is you look at the beam, and we're going to actually use method of sections, and we're going to look at just what's happening to the right of the left end, and just what's happening to the left of the right end. Okay? So here's our beam, and this is the left side. Okay. Here's the beam. Here's the right side. What's going on? We have an RL on the left side, and we have an RR on the right side. This is where we use the convention, though, because now we're talking about what's happening internally. So what is the convention? Which way do I draw the shear force? Yeah, I'm going to say down, okay, by convention. Which way do I draw the internal bending moment? Yes. Okay, which way do I draw the shear force on this right one? Up, right? Now that you got one of them, it's usually not so bad to do the other side. Okay? So that's the convention. This means that at the left side, V is equal to RL. Okay? What is M equal to? Okay, but that little distance is really, really small. Okay, TX. It's really, really small. It's 0. We're right at it. So that means that. So this, I see where we're going here, right? This is a really small distance. We're doing the boundary condition. It's right on the boundary. There's no distance between RL and where we're taking our M measurements. Yeah, okay. Did you say that already? Oh, I didn't hear you. I thought you said dx and not some other complicated stuff. Okay. So, okay, and then what do we do over here? This is V is equal to minus RR, and M is equal to 0. So now we go over to our graph, okay? And we say, well, we got some information now. We got some information. We're going to put we're going to put up here. We're going to do a. I'm going to use a different color. RL, sorry. RL, and we have that value. That's this one. Wait a second. Wait a second. Something is not right. Something is, what did I do wrong here? This is what happens when you go kind of by scratch. Oh, I have different notes here. Wait, hold on. I did it. Well, this should be RL. This should be it. Okay. I'm going to look at what I did yesterday. Yeah, this, why did it work out? Oh, slam. I drew the problem wrong. This is different. Okay, it's okay. It's okay. It's okay, but it's not okay. Last. All right. We have two decisions to make. We have one decision to make. Okay, we've just changed the problem. Yep. Okay, that allows us to keep, this allows us to do the same problem that's on the homework. All right, so it's like, okay, we could keep going through this, or we could just fix it here so that it's the same problem as in the homework. All right, sorry about that. So RL, it doesn't change anything here, but RL is here, okay, and the moment is 0 here. okay, on the left side. If we go to the right side, we have v equals minus our r, which is going to be down here. So let's put this right here. Okay. And this, actually, I'm not going to do that. I'm going to say, so look, we said, so v equals minus our r. We said that m app over, we have m app over L, okay, is greater than f app over 4, all right? So that means, okay, that, well, I'll make sure I got this right. RR B F app, okay. This is a positive, this is going to be positive, this is going to end up being okay. Goodness, how many different mistakes can I make? Okay. Is that good? V equals a RR, not minus RR. Okay? And so that's going to put, and this, we said this is greater than this, so this is going to make it positive still. Okay? All right? Like that. Any questions? And this one is 0. Okay, any questions on that? Yes. On the left side? No, because they're still opposite. Right? When we did the equilibrium, they're opposite. Guys, so thank you, right? This is good. You gotta fact check me, all right? I also have the responsibility to do it right. Okay, so now, what's happening in between? Okay, what's happening in between? That's the question. Okay, so if we look back at the problem, there's no distributed force between the left end and where we get to L over 4. Do you see that? There's nothing distributed here. And we have this equation up at the top, right? dv dx is equal to an external distributed force. So when we look at what's happening okay, from this region to this region, if dv dx, so from x equals 0 to L over 4, we have dv dx is equal to w, but this is equal to 0. So if dv dx is equal to 0, what does that say about the slope of that line? Flat, horizontal, good. So that's it, okay? Now, the other equation, right, is that dm dx is equal to v. So the integral, right, so if we do the integral, right, we get this. So we've got to integrate this expression from here to here. or we got to integrate this expression from here to here. And what's the integral of a flat line? Okay, yes, and that's true, okay. And what shape, what's the slope of that? Slope. So what's the slope of the line going to be here?
0.
No, the slope is RL, right? So it's a first order, right? We go from 0th order to first order, okay? And like you were pointing out, the value here, so we go up to this value, that value is, yes, the area of this, right? So this is going to be RL L over 4, okay? And it's going to slope like that, okay? It's a line. If you have a first order and you had to integrate it, what does that become? Parabola. There you go. Second order, right? Parabola. Okay, so we've gotten to L over 4. Now, at L over 4, there is the applied F-app. Okay? F-app is downward. All right? Downward means that it has a negative, or has a delta V that's negative. Okay? So it's going to drop by this F-app. Okay? So it's going to drop down. And let's just say F-app. Okay? What happens from L over 4 to 3L over 4 in terms of dV dx? Equals 0 again. Okay? What happens from x equals 3L over 4 to L? If we go back to the drawing. There's this M-app, but there's no distributed force applied. Okay? So it stays 0 as well. Okay? So what we can see is that this, just like it was here, is going to be another flat line. And so when we go from here to here, we just go with a flat line all the way to the end. Let's do it with a different color. Like that. Any questions on that? Now, what is happening from L over 4 to 3L over 4 with the moment? Well, we write the same equation again. Right? dm dx is equal to v. Well, what is v equal to? Well, v is equal to this RR. Okay? And that means it's going to have another slanted slope. It's going to be first order. But RR is less than RL. Okay, so the slope will be less, right? The slope, so we're going to get to some point over here. And the slope is going to be less. Yes?
I mean, that region, that vertical region on the V is not differential. How would he, is that like a open dot?
This,
Yeah, that.
oh yeah, well that's what we're talking about. This is the coupled force, right? The external applied force, the concentrated force, right? And that's where we get this discontinuity. Right here. Okay?
Yeah, but how are we just assuming that it's continuous?
Yeah, we're assuming that it's we're assuming there's a jump, so it's discontinuous, yes. And it jumps from, if you want to say, oh yeah, just left of L over 4, it's here, and then just right, fine. I'm still going to draw a line though, connecting the two. Okay. So this slope is less, we get over here, all right? And what happens at 3L over 4? We have our MAP. Okay, and so our MAP, right, we have a delta M, and is this a positive MAP or a negative MAP? Well, according to our convention, this would be a positive jump, and it's going the opposite, so it's going to be a negative jump, right? This one is going this direction, so it's a negative jump. So it's going to be delta M is equal to minus MAP, which means we've got a drop, okay? But we've got to get back to 0. And the slope over here is the same as it was here, positive. So this is a little bit of a nuanced thing. But what it means is that we drop down, okay, and this is going to be a minus, so this is going to be a delta M is equal to minus M applied, and then we're going to have the same slope. That's not actually that good. Let me do it a little bit better. I want to make it parallel to this. Okay. Like that. Okay, because this slope and this slope both are RR. Yes, Kevin.
So, just to summarize, from the graph of V, you were able to derive the slope for M from 0 to 3L over 4. And then the reason why it drops from the orange section of V down to below the x-axis is because there's a moment that you specify in the question that delta M is equal to M applied.
Yeah.
So that's why you drop all the way down. And
Yep.
then rise again with the same method that you used for the first two sections.
That's right.
Okay.
Okay. I mean, if you calculate out, if you have numbers, okay, and you calculate MAP, right, or you have, if you're given MAP, MAP will do exactly this. It will drop it below and make it negative.
The two other sections, there's no M applied. There's no M that you can use delta M with, because the only instance where there's a moment applied is at that point that you specified, right?
Right. So you can't use, yes. So let me say something a little bit broader. A concentrated force does not lead to a discontinuity in the bending moment. It leads to a change in the slope at that location, but it does not lead to a discontinuity in the bending moment. Just a discontinuity in the first derivative. Okay? A concentrated moment doesn't affect shear, internal shear force. And in fact, it doesn't affect it at all. Okay? Because it goes, dm dx is equal to v, but v doesn't care about m. Okay? All right. So that should save some time on, I think it's the third question for the homework. All right. And now you all get to have some fun. All right. Working on the homework. Thank you. Thank you for your patience. Yeah, I got hung up because I put this F app the wrong direction, and that made our lives a little bit tricky.
Would it have made the problem more solvable?
It would, no, the problem would have still been solvable, but the condition that I posed that M app over L is greater than F app over 4 wouldn't have had significance. All right? And it wouldn't have matched your homework problem.
Oh, that's nice.
Okay? For those reasons. Okay. Go for it. Okay. Question.
What's the year?
Can use my notes.
I'm on blank A4 as well also, but thank you.
I got 5. No, you can take it.
Banana boats.
Twice?
You know, like, all the time when I go to the gym and stuff. How many questions? 19, something 20. Oh, yeah. Yeah, no, you are.
I mean,
I thought I was. You guys are pro then.
No, it's like my schedule's so nice. Like, I have like the. Oh, because of Rex. Flash. You can't take me. I need one of those actually. Did a job. I think it's true. Oh yeah.
you know my life. You know my life.
Yeah.
I want to see my ex.
That doesn't look like a hairline fracture. That's not like a hairline fracture to me.
Oh, dude, I broke my collarbone and full on like sheared. Like, on the way up, I'm like, ah.
I'm so excited for this Euro. I think I'm gonna celebrate.
All right.
Treat myself.
Yeah, let's focus on the here and now.
What do you mean here and now?
Study.
Studying what?
Arrow.
I'm gonna do that all tonight. I'm gonna look over all the 4 chapters of notes. Apparently, chapter 1 and 2 go through pretty quickly. 3 is like the fundamentals, and then 4 is like when you get into the stuff, like meat.
The cool stuff.
Yeah.
Well, see you.
Stay away from me.
Oh, come on.
Pointed straight at an angle. Yeah.
To be fair, mine's not much better. I don't want my guy.
Alex, let me see.
Ow! Would you slap the cab?
I need to test it. I didn't pass the button.
I'm also tall, but not as tall as you. I do have like decent reading Yo. But my pinky finger is the same size as the Okay, well I have a nail. How's your way?
You gotta be confident in the ladies.
You got some spiders.
Oh yeah.
Spider.
No, dead. You're dead.
Oh really? No, I should have played piano. Play viola. That makes sense. You should play bass because you're tall enough, right? You need somebody like this tall who play bass. Then you have like a step son. That's bad. Not to mention they'll carry you around with really fun.
Big and short. Normally you would during the fall.
Adding average and still like.
I chose to do it during the spring semester.
I can't make my fall semesters the worst thing possible, especially because like well this way so what I'm saying is
But the L minus X,
that's this no, I can understand.
yes, but
I can't do it spring semesters. It's sad, you know, like seasonal factors or anything like that, or you know, like I like making my semesters harder than my spring, if that makes sense.
I like my other.
I can't do
So if I go, this is L minus, let's just say that it's L minus.
Yeah, spring is like.
Last spring was terrible. Like, okay, that, it wasn't too bad, but it wasn't like iterating towards having sense. So,
I'm saying you have to be very careful.
Oh, it's supposed to go good. Oh.
Here.
I think that's all this normally big. Like if you think about like my fingers are proportionally like small. Like compare your middle finger to like yeah, no, if I do that, it's like already touched. So, I don't know hand proportions. Yeah. I'll see you guys.
So it really is L minus X, right? Out here it's L minus L over 4, so that's not even 3L over 4. If this is the location you are, and you're saying L minus X, it's really starting from the right side. Because that would be X2 is another L.
Well, we could say that the distance between x and the end of the decreases as x.
So you need a different. My point is that it's coming from the right, so it's negative as possible.
But like, what is
Your point
and what is this point system?
is describing the location X you are in B.
So I thought my x is describing. Like,
When you use L minus X, it's not. That's what I'm trying to say.
no, what I'm saying is, if I take x as my position on the beam, this point, whatever else, this point is going to be.
3L.
No, that's just what I meant. That's L research paper.
what is this channel?
No, basic arithmetic.
Then you have to go there.
Well, I would never ever subject myself to so I'm overloading myself to false positive. Well, I'm joking because I'm like,
Here, right? If you're gonna use the same X that you have over here, right? This distance, right? This is 0 in this 3/4 system.
never
Based on X, based on itself, it has to be 0. This point, if I start this
fine.
point,
I understand that I could be much worse off. I'm very
so if
fortunate.
I define into your X2,
So you just want
What is
L minus X would be
because my laptop is dead, I'm sorry.
so this is how you define it. X2 is equal to L minus X.
Oh, you mean weight?
That's not, no.
No, not weight. It's not. You mean like load the
Relate,
load?
come on, relate internal transfer shear force to the external
Yeah,
distribution.
that's super load. Yeah, that's what it is. I didn't mean weight. So it's omega. I always wanted that W.
And I'm looking for all the moments coming this way.
We still need to, you have forces too, right? So you got
So I have a force here.
Hey, my hands are so weird now.
Yeah, his hands are bigger than
Yeah.
yours. Yeah, and that's crazy because my hands are smaller than yours. Yours are smaller than mine. So like, makes it even weird.
Like if I say
So how would it
my slice works, but then it has
Scaccioli also teaches mechatronics, right? Are you taking it? No. Are you using next semester?
so your X2 is
She, professor.
Huh?
She is Scaccioli.
Wait, don't we have it for dynamic?
Bro, this is just.
Oh, okay. Dynamic is pretty chill right now.
You actually need to see that. Number 2, I'm gonna Well, it's 2 weeks.
and one map is along the same.
Wait, did you need anything else? Flex for my flex.
Because what I'm
You don't. I'm not worried about it. You don't. But I'm trying to explain why you perceive this.
But you also use a negative expectation.
That's back in the way.
Yep.
I mean, like, everyone had and Chem 2, so that was like 8 difference.
Yeah.
That's
this
crazy.
seems to me is
I know.
this is a function.
Same with
Oh, so you're wait.
I did not.
Oh yeah, describe distance.
AB subscript. AB subscript.
No, I'm not. I'm just being
Well, in that case, it's moment.
With,
map for you. But you
What I did in college has to do with
It's not, it's like, you can count it when you get trying to sit down. You can't do it the normal way. It's 18. Yeah.
X is like so would it be true to say that the moment of this causes Oh, right. So if I say my slice is at X, right? Yeah, so in other words, overall. Right, so my slice is looking like, right? This is
Oh, yeah. Yeah. Right.
I would at this point, if I feel like, treat this as like, isolated signal, sort of like,
I expect a lot more culture.
I say, this distance.
Oh, you're
X. And that makes it crazy. Like that is
Oh, in terms of the original, sure.
right? And then I still have this force here. And so this moment, this force
Where's your moment?
being applied right here.
hopefully when we
And that moment, that force finds this distance.
Yeah, we got half that. You just got to
Very European.
Is it like they shattered your toe?
no.
Literally, the other part is an A. That's gonna be your moment from this like it's like a slice applied, like total moments on this slice being applied.
It's not a fracture, that's a break.
Minus this. Plus.
I mean, it's fine. You
So
I have to
if I
elevate
look
it.
at all this stuff, right?
Every time I take this down,
This here,
once I crushed it, I was like,
right? This,
Professor,
like,
Now it doesn't hurt.
now
then
it's
I'm
fine.
gonna have
It's still like pretty small, but like less.
but most of the stuff that are
That's cats from.
But this, remember this, two is
It's not being tied, more wrapping.
I guess they go slow, but it's kind of fine.
Every time I see you have to think. He's on the table with your hands with food in your mouth.
Okay. I just know that.
I'm still using this, I'm still like.
Every day.
Every day, I just look at the slice. This is like, examples, I just look at the slice and X.
You can't take it off,
Is
right?
variable that
Not
happens.
just get off.
When you say.
I don't count.
Actually,
I don't count it down.
Whatever, the point is, I have X. And I
I
can
want
determine
to see you without
my moment in terms of X.
Right, you're wrapping up there.
I hope, like my
And
foot.
I can also take the.
Can I see one right now? Can I see it right now?
So that just like.
When you're walking up, watch what's happening.
You want to see me barefoot?
That would change.
Now? I know. No, I can do it right now. That was weird though.
looking for 50 years at Rock. Bro, that was so
Come on.
funny.
Come on. I don't want to wear sneakers. Trying to wear sneakers.
That's another thing. I'm actually very surprised that you're able to do that at 40-degree weather.
Is it like?
My foot.
Yes.
It's not 40-degree weather yet. Alright? 15 Celsius. So that's over 15. That's like 6, that's like pretty much 60 degrees weather.
If I find X2, L minus X, then yes, I have X2. Then in that case.
We can go through this.
In that case, I would have positive.
Right. And so, we're taking slices, we've got. Nonetheless, right, we know that there's going to be a change, right, of course. It's going to drop down, but it's still above. And it's going to end up here. I just fucking want to go. And if you want, okay, you can define, you can use method of section as well. But I invite you to, you know, our class, that happens to be now of the things.
Like I'm saying,
Right, so you know, the avoid controversy, right? As you're moving along. The avoid controversy, you everything nice and normal. As you, make this text, right? You open up here, and you have our F back here. Alright, and you have this here. Oh, that's already fine, right? And then you use the extension here. Yeah, and you will get that V is still positive. Okay, if you plug in all the numbers, you will get this. Remember the NF is in.
Yeah, because this comes from,
No,
the V comes from the, I had a senior kill this.
Yeah, well, RL, right, exactly. So you have two equilibrium, right? And RL minus F minus B. Right? So V is equal to RL minus F. Right? And what is RL? RL was.
Because RL was this. Because I have my zero there. So my RL would be this.
some things that if I have more comments.
You should fucking do it.
Listen, an A over.
said, not sure that'll be possible. Okay, because we do this thing out.
Is it went down?
I was just talking about like my schedule.
No, it's internal. This is the prevention. B is positive. We have to have that, right? Right? So this is gonna be minus F apple plus M apple over L. And in the beginning of the problem, we said that M apple over L is greater than. So, if we do it just from the left side, using the same x in this condition, so it's coming out of the face of the convention, like I said, it comes out. The other way is fine too, but it's very confusing, and it's, what we have to do is we have to. And what I'm saying is your negative is not wrong, it's just it's coming from the right, which means it's positive if it's coming from the left. That's all.
The other thing, I have here, like, I find it both ways, like slice, right, like this, or slice on the left. My slice on the left is, this was sometimes X, so times distance, right? My slice.
Look, if you want to keep it simple, just define x coming from the right, and then take the slice again. And the left is fine.
I used to code
You want to make sure that the axis is coming out of the face that you define, so that you can use the connection. Okay. Alright. Like you're good.
Oh, you guys. Dude, I think honestly,
Yeah, let's look at that. So this is just the L. Yeah, that's good. Okay, so this is good, right? This is derivative. So negative slope. That's good. So what is going to happen? If you want to figure out the moment here and here. Comes up?
You didn't really go to the exam.
I didn't look at it. I didn't know.
You got like a 95.
how did I help you?
You were really good. Just, you did great. You did Jeffrey, right? Yeah, I did college. Okay, never mind, you did not transfer.
Right, so it's not using derivative of the moment. Zero. Derivative of the moment.
It's spelled the same.
Yes.
Right, so you're integrating this to this, but you're coming from the left, you only integrate to
All the.
Yep.
If not, you might.
Yeah, I know. I was saying, like,
Or it's not quite.
Joy.
Oh, 0.75. But you're only on the L, right?
No, I haven't thought of that last time.
That's what.
Actually, I didn't. Unity does.
Oh, okay.
What is he supposed to?
He said he's not.
Yeah.
I'm telling you, when you're at, it's pretty straightforward. So like, I understand everyone. Give it kisses. That's why we'll give it. Are you got You're not going to.
Bro, we can walk with this.
This is dude, you're talking about it's like social media. How do you do? Did he have tomorrow? He had tomorrow. So then, does he have?
Oh, so it doesn't match up.
You should ask him for this.
So that's why.
Professor, because listen,
So I can.
if he has access to this,
Just focus on
the file might be there.
So if he doesn't roll my these extra.
I'm saying like specifically kids.
If this is right here, and this is all and it's on a cantilever. So it's right. So I don't know.
They're all college age. Oh, you listen to one of those random houses. In the arms, with the rest of the season. Yeah, like. I'm joking when I say that. They're my life. I know, my mom's gonna kill me to get that silly hair. That was just they were moms. They look nice. I just throw it.
Okay. Yeah, so you mean formal plus, so AP will maximize Yeah, what I mean is like, this is the weight, this is the, you know, it's going this way, so that means there has to be a reaction this way. So the moment here is maximized, there's no moment here, it's because, like, you can set the moment, so okay, moment here must be maximized, because, you know, like, right here, it's going down.
Oh, like, think about the name.
Assuming that you define it as
It would be here. Okay. So that's where the moment apply is maximized, or the reaction moment is maximized.
Yeah, so whichever product you come across, maximum moment will occur where your force is maximum.
This is not.
So you have to make slides over there. Yeah, what's up?
Oh no, yeah, it's okay. There it is. It's added. Yeah.
discussion with them, so. Wait, is it?
So what's next? Well, that's not the max. Well, no, it gets you more than that.
What's the
Get to L2, right?
Actually, I think it's just going to be,
You see that has a different slope.
I think it's just gonna be more like the most, the most orientation.
So
Yeah, it is.
this
Powerful.
that red, this is the yellow. That is going to be
Just deriving a cost.
RL times L.
This is Rebecca, same engineering.
I don't know, she was in the workshop.
Oh, yeah. Okay. This is something
See ya.
Oh, that's the interval.
Thanks.
The interval, the area here, right, is RL times L. Right, so that's what we get to this. We get to this one, right, so we have a difference. This. So essentially, we have the table we had there, and now we add L2 minus RR. Right, it's essentially an interval product, we want to take the area. Forget the math, let's look at the graph. Right? We want to take the area under this portion of the curve. You know,
That's what we do. No, not the exact, that is the.
So, 3 over 4 minus L. Right. Right. Plus. Right. That is. RR. Or RL, right, plus RL. Yeah, no, L over 4. No. RL is this one. So RL times L over 4 plus RR times L over 2. Just write out, right? We're trying to forget all the math, forget this equation. What's the area of this right? Right. What's the area of the rectangle between L over 4 and 3L over 4? Right. And we want the polar, and it's out of this together. Then you solve, yeah, exactly, then you solve for those. Does that make sense? Okay, yes, you have a question? Okay. Okay. So it's no, it's not just a matter of trying to solve a different problem, right? This one, that problem had a, right, so this one is a cantilever. This one is, and
That's false, because I was back.
right, so you have to, you do the whole process. Right, you can't, it won't possibly be local. So the first thing is to external equilibrium. Right, and then go about, losing the, so once you got external equilibrium, then you have those forces. And then you can go about using the x, y, and z. Right, and then you calculate the
don't care, well, you don't really care about it, because it's just asking for the maximum. So the maximum is up here. That's right. And you're not integrating this, you're integrating this. Whatever that point is what it is. That's right. Okay, no problem. Oh boy, okay. I gotta go, I'm supposed to be at this other meeting.
Quick question. For the third problem, they just have to make a slice and that's it, right? Where the force is applied. That'll be the maximum.
Nope. Nope. Hold on, let me shut off the video.